Welcome to this explainer. Artificial intelligence often gets treated like some kind of magic black box. But once you look past the hype, it's actually a highly systematic toolkit. Today, we're breaking down the 5 core ways machines actually learn from data. We're going to move entirely beyond that illusion of magic to understand exactly how these systems are built and how they get better over time.
So let's jump right into this foundational mystery. Why do we need 5 different ways of learning? If machine learning is just learning from experience through data, why wasn't one single method enough to build AI? Well, it reveals a fundamental truth. The real world is incredibly messy, and the type of data you happen to have completely dictates the tool you have to use. Let's start with the most common method. Think of it kind of like a student with a really hands-on teacher. Imagine a kid taking a math test. The teacher is right there, explaining the lesson and immediately providing the right answers. Every single time the student makes a mistake, they get corrected on the spot, so they never really learn alone. We call this supervised learning. Your data set is literally that teacher. The key here is that every single piece of input data comes explicitly paired with a correct output or label. The machine makes a prediction, compares it to the right answer, measures how wrong it was, and then adjusts itself. This is absolutely the engine behind the tech we use every single day. It's how your inbox filters out spam, how your bank instantly flags a weird credit card swipe, or how hospitals are spotting tumors in X-rays with superhuman accuracy. Because doctors have already labeled thousands of historical X-rays, the machine learns the general rules to diagnose brand new patients.
Supervised learning is incredibly powerful for sure, but we run into a massive roadblock. What happens when the correct answers just don't exist? Gathering massive amounts of data is usually pretty cheap, but paying experts to sit there and label it all, that's incredibly expensive. Imagine a supermarket with millions of customers, but nobody has categorized how they shop.
It's exactly like walking into a massive library where thousands of books are just dumped all over the floor. You've got no labels, no shelves, and no librarian to help you out. But even without a guide, if you just start looking at the covers, you'd naturally start putting the history books in one pile and the science books in another. You organize the chaos just by looking for similarities.
This brings us to unsupervised learning. Since there's no teacher and no answer sheet, the algorithm's job isn't to predict some known outcome. Instead, it explores the raw data completely independently to uncover hidden relationships. It's how Spotify figures out which listeners have similar tastes, or how marketers find hidden buying patterns without ever being told what to look for. The contrast between our first 2 paradigms is pretty much night and day. Supervised learning relies on absolute, known truths and explicit guidance. Unsupervised learning? That's about solving a puzzle through pure, independent discovery. 2 totally different problems, completely dependent on whether you have those human-provided labels.
But the real world is rarely that black and white. More often than not, you're stuck in this frustrating middle ground. You might have millions of raw medical images, which, again, are cheap to collect, but maybe you only have the budget to pay expert radiologists to label, say, 5,000 of them. So the rest are just sitting there, totally unlabeled.
Think of this like a massive lecture hall with 1,000 students, but only 20 of them actually have a teacher to explain the lesson. Once those 20 get the core concepts, they turn around and share what they know with the other 980 classmates. That massive, unlabeled group learns the overall subject by mixing that tiny bit of instruction with their own independent work. We call this semi-supervised learning, and it is a brilliant compromise. It saves tech companies millions in human labor while still getting world-class results. The AI uses that tiny fraction of human-labeled data to get its bearings and then maps those findings out over the huge, unlabeled pool. It is a literal game-changer for stuff like autonomous driving.
Okay, so that covers static datasets like spreadsheets and images. But what about tasks that require active experience? Can a machine learn entirely through physical experience and consequences? Think about a robot learning to walk. You can't just feed it a spreadsheet of joint angles. It has to actually interact with the physical world in real time.
Think about it. You literally cannot teach a kid to ride a bike by handing them a manual. They have to actually get on the bike, try to pedal, and inevitably fall down. Every success builds confidence, and every scrape provides a pretty crucial lesson. They adjust, they try again, and eventually they balance purely through continuous trial and error. Enter reinforcement learning. It operates entirely on actions, consequences, and rewards. It's honestly a lot like training a dog with treats. We drop the AI, which we call an agent, into an environment.
We don't give it the right answers. It just has to discover successful strategies through pure interaction, aiming to maximize its rewards and minimize its penalties over time.
It all comes down to this continuous feedback loop. The agent makes a decision, takes an action, and the environment pushes back with either a reward or a penalty. The AI is constantly wrestling with this dilemma of exploration, trying wild new things to find better strategies, versus exploitation, which is just using the best moves it already knows. This is exactly how computers beat world champions at chess.
Right, so that brings us to the final massive hurdle. If we want an AI to understand all of human language, history, math, poetry, everything, how do we pull that off? We can't afford to manually label billions of web pages, and creating a reward system for all of human text would take centuries. So how exactly did something like ChatGPT learn?
This roadblock actually forced arguably the greatest breakthrough in modern AI. Researchers realized that language already follows natural rules. Words appear together in predictable ways. So instead of needing human labels, they set up a system where the learning objective is generated automatically from the raw text itself. The data literally becomes both the textbook and the teacher.
It's basically a massive game of fill in the blank. Like if I say, the cat sat on the, well, you can guess the next word is probably mat. By playing this game trillions of times across the entire internet, hiding parts of the text and forcing the machine to predict the missing words, the model naturally absorbs grammar, facts, and human reasoning all on its own.
We call this self-supervised learning, and it is the secret engine powering the massive language models we use today. By automatically generating its own tasks from unlabeled data, it totally bypasses the need for humans to label anything. It develops this incredibly rich understanding of the world before we even ask it to do a specific job. All right, let's tie this whole thing together. Think of these 5 paradigms like a carpenter's toolkit. A hammer is great for nails, but it's terrible for cutting wood, right? No single machine learning method is magically better than the rest. They're just different tools built for entirely different jobs, depending on what kind of data you actually have.
So here is your complete framework. Got labeled data? You grab supervised learning. Just raw unlabeled data? Unsupervised. A mix of the two? Semi-supervised. If your AI needs to physically act in an environment, that's reinforcement. And if you have internet-scale text or imagery, you unleash self-supervised learning.
And there you have it. You now see right past the illusion of magic, straight to the actual mechanics of how machines learn. We aren't limited by human labeling anymore. We can leverage the entire digital output of humanity to train these systems. So the only question I have left for you is, what problem are you going to teach them to solve next?